Hello, everyone. Thank you, Faisal, for the introduction, and thank you for joining. I'm Habiba from Purdue, and today I'll be talking about our work on secure group pairing for IoT devices. So, Internet of Things, or IoT, connects millions of devices that monitor and control several private aspects of our daily lives. And to enable their functionality, these devices exchange vast amounts of information, such as sensor measurements and actuator states, that can reveal sensitive information about the user and their environment. To protect these data exchanges between devices from eavesdropping attacks and middle-person attacks, pairing mechanisms exist that establish secure cryptographic keys to enable secure wireless communication among these devices. Now, traditional pairing methods that most of us are aware of or use it typically involve user actively participating in the process. So to pair your phone with your watch, you're typically required to enter a PIN code or a password or bring the devices together and perform some sort of gesture. However, these approaches are becoming more and more difficult to scale as the number of devices in our deployments continue to increase. Moreover, several IoT devices like surveillance cameras or voice assistants do not have the keyboard or keypad interface to support the traditional pairing methods. To address these limitations, recently a new domain of device pairing has emerged that leverages the fact that IoT devices continuously sense their physical environment. And they can use this physical context to derive a shared secret and establish secure communication channels through cryptographic keys. For instance, two microphones in a smart home will both record the sound of a door opening or closing and can use that as a shared secret to bootstrap a key establishment protocol. The good thing about such context-based pairing solutions is that they automatically provide resilience against an outside attacker that cannot observe the physical context, that is, the events occurring inside the physical environment. Now, while these approaches eliminate user involvement, most of the existing approaches only work for devices equipped with similar sensors. So if we wanted to pair a motion detector or a temperature sensor in this scenario with the microphones, we would need to equip them with a microphone such that they can also record the same sound and derive the same shared secret for key establishment. To make this to be effective in realistic IoT environments, context-based pairing systems must be able to pair devices with heterogeneous sensing modalities. And to make this more clear, let me show you a scenario where we want to pair an Alexa speaker with a temperature sensor and a power meter. Here, I'm showing the sensor measurements recorded by these three devices in response to some commonly occurring events in IoT environments. If you notice, all three of these devices observe some events in common. However, their signal characteristics vary significantly from each other, making it infeasible to directly compare these sensor measurements and establish a shared secret. To address this limitation, a recent work proposed Perceptio that leverages the idea that events that are observed in common by these devices will be observed at the same time. And by using the inter-event timing, that is the time interval between consecutive occurrences of a given event, they can derive a shared secret and use that to bootstrap a key establishment protocol. While this approach addresses the problem of heterogeneous IoT devices, there are several limitations of this work. First, it only pairs instantly influenced sensors, so devices that measure continuous physical quantities like temperature, humidity, or pressure cannot be paired using this approach. Second, its pairing process is impaired by simultaneously occurring events, and it incurs a long pairing time when multiple events occur simultaneously. Lastly, it only pairs two devices at a time. So with the growing number of devices in our IoT environments, it incurs a high computation, communication, and energy consumption overhead. So based on these observations, there is a need for a pairing system that pairs heterogeneous sensors with instantaneous and continuous modalities, accurately derives context, and establishes group keys among devices that are sensing the same context. So to address this research gap, we present IoT Cupid, which is a secure group pairing system for heterogeneous IoT devices. On a high level, IoT qubit begins by processing the sensor measurements in a way such that it can derive the events detected by these devices. From the detected events, it extracts temporal sensor features and groups them into multiple clusters based on the event type. And from these detected event types, it extracts inter-event timings, which are then used as an evidence of co-presence to bootstrap IoT qubit's group key establishment protocol. Now, the first challenge in implementing IoT qubit is that how can we accurately derive context from the IoT environment? To make our system usable, we consider event as anything that is naturally occurring in the IoT environment, resulting from users' activities like walking, making coffee, or opening and closing a door. And for detecting the events, we can apply a window-based threshold detection approach, where we leverage a lower threshold to separate the impact of the events from background noise, and then apply an upper threshold to remove high-amplitude noise signals. Now, this approach works for instantaneously influenced sensors. However, there are several devices that measure physical quantities that impact the sensors with a delay, and this delay may vary over time based on several different environmental conditions. So to deal with this, we use a derivative-based event detection approach, where instead of applying the thresholds to the raw sensor measurements, we apply them to the rate of change in the sensor measurements, such that we can detect events for both continuously and instantaneously influenced sensors. Once we detect the events, IoT qubit then extracts inter-event timings from these detected events to use as an evidence of shared context. Here, we leverage the fact that a single event may impact multiple devices. For instance, a door open or close event will impact sound, luminance, temperature, and humidity sensors. And all these devices will observe this event at relatively the same time. So by using the interval between consecutive occurrences of this event, all these devices have a shared secret that it serves as the proof of co-presence for these devices. So given that in IoT environments, multiple devices detect many different types of events, and before the key establishment protocol, these devices do not know the type of events that may occur in an environment. So we leverage clustering approaches to separate these detected events into their different types. And for this, we extract temporal sensor features from the sensor measurements and use them for clustering. Here, one challenge is that in typical IoT settings, multiple events may occur at the same time. For instance, a door open and a coffee machine on event may have an overlapping impact on the sound sensor. And this overlapping impact is very different from the impact of these devices, this event on these devices in isolation. So if we use traditional hard clustering approaches like k-means, the number of detected event types will be inaccurate, leading to incorrect inter-event timings and hence longer pairing times. So to address this, we leverage fuzzy c-means clustering approach, where we assign each event to multiple clusters with a degree of membership using the fuzzy clustering objective. This allows even simultaneously occurring events to be appropriately clustered to their appropriate event types. Once we have separated these events into their types, we extract the inter-event timings and then use them in IoT qubit's group key establishment protocol. In our key establishment protocol, all devices that sense the same set of inter-event timings for a given event type can establish a single shared group key and use that for all communication instead of encrypting their messages for each device individually. For our group key establishment protocol, we extend a partition group password authenticated key exchange protocol that uses the inter-event timings as a password, which are encoded in order to address minor deviations in the inter-event timings. The partition group password authenticated key exchange then uses these passwords to bootstrap a group key between all devices that are sensing the same set of events. Our protocol is resilient against middle-person attacks, where even if an adversary tries to intercept the messages between the legitimate devices, since the legitimate devices encrypt their public keys with the password, which in this case is the inter-event timing, an adversary cannot extract them. Moreover, our protocol also offers resilience against brute force password enumeration, where an adversary tries to guess the password and participate in the protocol due to the hardness of the elliptic Diffie-Hellman online session in our protocol. Because our system is resilient against brute force enumeration attacks, it only requires 32-bit entropy in the inter-event timings, and hence, compared to fuzzy commitment approaches that require 128-bit entropy, it offers 4 times faster pairing times. Now, IoT environments are dynamic, and device addition and removal is a really common thing. So to support new devices being added to the environment, IoT Qubit offers reinitiation-based key management strategies where a new device entering triggers all devices to start extracting inter-event timings and participate in the pairing process. Similarly, we perform a periodic liveness check to revoke the keys of any failed or inactive devices. Here, I want to know one thing, that since IoT Qubit relies on commonly observed events to derive group keys among devices, there may be a case where two devices do not have any commonly observed events. In this case, IoT Qubit supports group-to-group communication through intermediary devices, where one device that belongs to multiple groups can facilitate communication between them. Now, let's take a look at IoT Qubit's evaluation. So we performed 2 real-world studies in a smart home and a smart office with multiple sensors and actuators, and users' routine activity triggering different events. We also simulated an adversary by placing devices outside the environment's physical boundary. In terms of pairing effectiveness, IoT Qubit can pair all devices that sense similar events. Here, I'll show you just some examples in our experimental setup. So for instance, the door open or close event is detected by sound, luminance, temperature, humidity, and gyroscope sensors. And all these devices derive a single group key using only 4 matching inter-event timings. Similarly, radiator on event is used for pairing sound, temperature, and humidity sensors. Interestingly, even though the power meter does not sense any common events in most of the devices, it uses the sound sensor as an intermediary device with IoT Qubit's group-to-group communication to talk to the other devices. In terms of efficiency, IoT Qubit only takes 39 milliseconds on average to derive a secure group key among 20 devices with 4 event sources, and this overhead only increases linearly with an increasing number of devices and event sources. Now, I mentioned earlier that our group key establishment protocol provides resilience against a polynomial time adversary launching middle person or denial of key exchange attack. We also evaluate its effectiveness against eavesdropping attacks by measuring the event detection accuracy for an adversary that is present outside the physical boundary of the IoT environment. And we find that there is a significant difference in the average precision and recall rate for legitimate and adversarial devices. And because of this low detection rate, an adversary cannot extract sufficient inter-event timings to participate in the pairing protocol and hence derive the group key as of the legitimate devices inside. So to summarize, IoT Qubit is a secure group pairing system for heterogeneous IoT devices that can pair a variety of sensors with different modalities. It provides 4 times faster pairing rate and supports dynamic device addition and removal with group-to-group communication. Thank you for listening, and I'd be happy to take any questions.
Do we have any question? If not, I want to ask one question. So if any of the device got tempered or something, then is there any way to detect that? So.
Yeah, that's a really good question. Thank you. So if there is this problem of detecting compromised devices by profiling the behavior and intrusion detection and so on. So a system like that can easily fit in with our approach. We also perform a liveness check in case some device has experiences of failure or is compromised. But we treat that as okay, all the devices within the environment are trusted.
So yeah, thank you. Thanks again. Oh, there is one question.
Did you assume a noise-free communications environment?
You mean noise as in?
Communications noise.
We didn't focus on the communication we assume that the communication channel is like a standard communication channel like Wi-Fi or something. So if there is noise, I don't think it would affect it because we're just sharing the inter-event timings. But an adversary launching a middle person attack, we consider that where they're trying to inject packets or something.
Hi, really good work. My question is, in IoTs, in smart home setups, it's very common for a device to be moved across rooms.
Yes.
So how do you think your model will adapt in such a scenario where the modalities may change from one room to other?
Yeah, that's a great question. Thank you. So because this pairing method is supposed to be supposed to occur when the devices are initially installed. So if a device is removed and installed in a different location, the pairing method would be triggered again, and the inter-event timings would be based on the new events that the device is sensing. So it's basically like a reinitiation approach. Thank you.
Great. Let's thank again Habiba. Thanks for the nice talk.